Nevertheless, the tar sands are a very large and valuable resource and may be exploited for hundreds of years. The production rate is even worse with oil shale. Oil shale is a rock containing an organic material called kerogen that converts to oil when heated to about 500 degrees Celsius. Estonia, Russia, Brazil, and China currently mine oil shale. However, production is declining due to economic and environmental factors. Heavy oil in Venezuela can be converted to oil suitable for refining after extraction and upgrading. Again, production rate is the problem, as investment in huge facilities is required. Deep in the ocean, there are huge quantities of methane hydrate, which is natural gas held in a matrix of water just above freezing, deep in the ocean. Undersea mining is difficult. There are no current recovery operations and none expected for a few decades. Again, huge investment and facilities for recovery and conversion to liquid fuels are required, and production rate is likely to be small compared to demand. The production rate of liquid fuels from unconventional oil is likely to continue to be far too small to meet demand, and for the longer-term future, all are finite and expendable. This line displays the actual oil we have produced to date. The United States Geological Survey predicts 3 different dates for peak oil, based on the probability of increasing recoverable reserves. The first date is 2026, with a 5% probability that the peak will be reached by then. The second is 2037, with a 50% probability that the peak will be reached by then. That is the same probability as flipping a coin. With oil being so important, to count on reaching 2037 is not a good bet. The third is 2047, with a 95% probability that the peak will be reached by then. Peak oil occurs when the maximum possible production rate of oil is less than consumption. When we reach peak oil, what role do you see unconventional oil playing, such as the tar sands or oil shale?
Unconventional oil will always have a small role in world oil supply. It is important to understand that reserves of unconventional oil are not related to production rate. Synthetic crude oil cannot be produced fast enough from unconventional sources to come anywhere close to meeting even current world oil demand.
But won't increased oil prices actually extend the supply?
Yes, but not by much. A few new oil fields may be found in difficult-to-reach places, such as the deep oceans. The amount of oil in a field is fixed and will not increase with higher prices. As the production rate from an oil field diminishes, smaller production rates become economically viable with higher prices, and a bit more oil will be recovered than if the price were lower. Much, if not all, of the easily recovered oil has been found. That's why offshore oil was developed, and also explains why there's interest in unconventional oil. There are no perfect alternatives for any of the fossil fuels, and certainly not for the liquid fuels from oil that are vital for road and air transport. There are some alternatives to liquid fuels, but they are really only small niche applications and are not available on the current scale of about 100 exajoules per year, or the equivalent of about 700 billion US gallons of gasoline worldwide. There's the concern for scale again. Considering the importance of oil, it would be prudent to start preparing now for shortages of liquid fuels. The date of peak oil production may not yet be known with certainty, but it may occur at any time. It is essential that we view the situation realistically.
If there were no carbon dioxide in the atmosphere, the Earth's atmospheric temperature would be minus 18 degrees Celsius, and the Earth would be a frozen planet. There is a correlation between carbon dioxide and the Earth's temperature. The ice ages correlate with a carbon dioxide concentration of about 180 parts per million. concentration was about 275 parts per million when the ice melted and most of the planet became habitable by humans. Today, the concentration is about 380 parts per million. The record of this correlation goes back for 400,000 years based on the Vostok and Sipil ice cores taken in Antarctica. The benchmark is 550 parts per million and twice the level of 275 parts per million in pre-industrial days. It is often referred to as double carbon dioxide. It is a benchmark used by scientists to estimate how much doubling the concentration of carbon dioxide in the Earth's atmosphere would affect atmospheric temperature, climate, and other factors. As late as the early 1980s, some scientists were predicting the Earth was about to enter another ice age. These predictions began to change as a result of measurements of the concentration of carbon dioxide in the atmosphere at Mauna Loa in Hawaii, started by Charles Keeling in 1959, when the annual average was 315 parts per million. As the average increased in the following years, people began to realize the extent to which carbon dioxide concentration in the atmosphere was rising. All other factors being constant, an increase of carbon dioxide in the atmosphere will warm the Earth's atmosphere. The Intergovernmental Panel on Climate Change, Business as Usual Scenario, IS 92A, represents an estimate of the rate of carbon dioxide increase in the atmosphere if fossil fuel consumption continues to grow as in the past. On this path, carbon dioxide concentration will meet the 550 parts per million benchmark by about 2050. The Kyoto line, calculated by James A. Edmonds, represents the estimated rise in carbon dioxide levels if all of the countries that signed on to Kyoto were to meet and maintain their commitments. This path would delay reaching the benchmark of 550 parts per million by about 10 years, or to about 2060. The level of carbon dioxide would continue to rise above 550 parts per million at the annual 1990 rate of about 1.5 parts per million. This rate is likely to increase because more than half of the world's population has not signed on to Kyoto, and they represent the greatest potential for increase in energy consumption per person. The only control we might have over the atmospheric temperature would be to limit the rise caused by carbon dioxide by eliminating or sharply reducing carbon emissions. It appears that the lowest level that we might have a chance to achieve would be double carbon dioxide, because replacing fossil fuels will take a long time. Since pre-industrial days, there has been a smooth 35% rise in the concentration of carbon dioxide in the atmosphere. However, a history of atmospheric temperature shows that, at a given level of carbon dioxide, atmospheric temperature can fluctuate widely by several degrees. The Earth's temperature does not react smoothly to an increase in carbon dioxide concentration because, from time to time, one or more natural factors can temporarily override its effect. Several natural variables affect the world's atmospheric temperature. Carbon dioxide is the most important of the greenhouse gases and nourishes all plant life, which is at the bottom of the food chain. Under certain conditions, water is a more powerful greenhouse gas than carbon dioxide and contributes to keeping the climate warm enough for us to live. However, on any given day, moisture as clouds can be reflecting sunlight or retaining heat. Radiation received by the Earth from the Sun varies according to variations in the Sun's energy output, the distance the Earth is from the Sun, and variations in the Earth's declination. Sulfur aerosols and dust from volcanic eruptions lower the atmospheric temperature by reflecting the Sun's rays away from the Earth, and volcanic gases warm the atmosphere. Methane is a natural and small component in the atmosphere, and about half comes as swamp gas from wetlands. its effect is small in comparison to that of carbon dioxide. Although it has about 20 times the warming effect of carbon dioxide, it breaks down to carbon dioxide and water in about 10 years. Several man-made variables affect the world's atmospheric temperature. By far, the largest of the man-made sources of atmospheric carbon is carbon dioxide from the production and burning of fossil fuels. Methane is a smaller factor and is released by several human activities such as farming of ruminant animals, such as sheep, where part of their digestion is a fermentation process that releases methane, as well as growing rice or burning wood and other biomass at too low temperature. The use of Freon is phased out by the Montreal Protocol since 1987 because alternatives are available. Sulfur aerosols reflect sunlight and are discharged to the atmosphere when the sulfur in fossil fuels is burned. Nitrogen oxides from the burning of fossil fuels have a warming effect. The green baseline for this graph is the average of the green dots, 1961 to 1990. An example of the effect of naturally occurring factors can be seen by the 3 red dots just above 1990. The upper one is the temperature of the Earth's atmosphere in 1990. The middle one is the temperature in 1991, which was reduced by discharges from the eruption of Mount Pinatubo on June 15, 1991. Sulfur aerosols and dust reflected sunlight and cooled the atmosphere. The lower red dot shows further cooling in 1992. Another example of the effect of natural factors can be seen by a drop in atmospheric temperature between about 1940 and 1970, even though the carbon dioxide concentration increased by about 25 parts per million, or 8%. In spite of the variation, for one or more reasons, there is a measurable increase of about 0.8 degrees Celsius in the Earth's average atmospheric temperature since the late 19th century, when the atmospheric concentration of carbon dioxide was about 295 parts per million. How much will increasing the concentration of carbon dioxide from 275 parts per million to 550 parts per million raise the Earth's atmospheric temperature? The estimates range widely from 1.5 to more than 4.5 degrees Celsius. Just from doubling of carbon dioxide, the temperature rise should be about 1.5 degrees Celsius. Figures above this are the result of estimates of the effect of feedbacks that magnify the temperature. The current debate is over the magnitude of the feedbacks. There is no argument that atmospheric carbon dioxide levels are rising. They have been measured directly since 1959, and this is clearly the trend. However, there has been some debate as to whether this causes global warming. What is your position on this?
All other things being equal, increasing the concentration of carbon dioxide in the atmosphere from the 275 parts per million by volume in pre-industrial days to 550 parts per million will increase atmospheric temperature by about 1.5 degrees Celsius. How much warming will actually occur depends on how the feedbacks work. For example, temperature increases may trigger something that raises the temperature even higher. A major concern of scientists today is to try to determine feedback factors and quantify their effects. There is no doubt that there is global warming. Even the changing arrival dates for birds and the northward expansion of butterfly ranges are telling us this. The only question is about how much warming will occur. If atmospheric temperature rises by 4.5 degrees Celsius or more, and there are serious negative effects, then we will need ample energy to adapt. If, on the other hand, the increase in temperature is about 1.5 degrees Celsius, warming may not be as serious a problem.